Welcome to this lecture. This is the sixth and final lecture of week 4. In this week, we have looked at some further properties of the three modes of convergence for random variables that we have discussed so far. Just to recall, the three modes of convergences that we are considering are almost sure convergence, convergence in LP and convergence in probability. We have also looked at certain further properties involving finite sums of random variables and series of independent random variables. So, that is what we have discussed in this week. In this lecture, we are going to talk about certain exercises and problems involving the content of week 4. Without further delay, let us continue the discussions using the slides. All right. So, as always, we will denote by omega f p a probability space. All the sequences of random variables that we considered will be assumed to be defined on this probability space. So, first we discuss the solution to exercise 1. So, the exercise 1 asks that the continuous mapping theorem is not true for convergence in this LP space setting. In particular, we are going to look at the L1 convergence and show that for some specific continuous functions, the convergence for the new sequence after applying the corresponding continuous function does not hold. So, let us see. So, in our earlier discussion on week 3 in note 9, we had discussed an example of a sequence of random variables such that x n's converge to x in the L1 setting, but with the additional structure that the second moment of x is infinity. In this case, we immediately will have that x n squared does not converge in L1 to x squared, because x squared itself is not in the L1 space. So, therefore, we immediately conclude that if we look at the continuous function x going to x squared and apply it to the sequence x n converging in L1 to x, then the resultant sequence is not satisfying the property that it is going to converge in L1. So, therefore, in general the continuous mapping theorem is not true if we are considering this type of LP convergences. All right. So, let us move on. So, we now discuss the solution to exercise 3. So, here we are talking about uncorrelated random variables, but recall that independent random variables are always uncorrelated, but the converse is not true, and the exercise asks us to construct explicit examples of uncorrelated random variables which are not independent. So, let us look at some explicit random variables in this case. So, we start with a random variable x which has the uniform distribution on -1 to +1, and look at a new random variable y defined as mod of x. So, it can be immediately checked that the distribution of y will be uniform over the interval 0 to 1. So, please check this. Now, let us look at the setting about the uncorrelatedness of these random variables x and y. So, here we look at the expected value of x times y. Remember, y is nothing but mod of x, and therefore, this quantity, the expectation, can be computed in terms of the corresponding integration involving the corresponding probability density function of capital X. Now, capital X has the probability density function given by half on the interval -1 to 1 and 0 otherwise, right. So, therefore, we can immediately compute this integration, and here you note that the integrand is an odd function, and therefore, on this symmetric interval -1 to +1 the integration will turn out to be 0. So, therefore, expected value of x y here turns out to be 0. Now, let us compute the covariance. Here you note that the random variables x and y that we are considering are actually bounded random variables, and it will have all moments. So, therefore, there is no problem in talking about this kind of calculations involving expectations. Now, here we look at the covariance which has this formula that it is expected value of x y minus the product of the expectations. Now, here expected value of x y we have already computed to be 0, and also note that x has the distribution which is uniform over -1 to +1. Therefore, expected value of x is also 0. So, therefore, this whole quantity turns out to be 0. So, therefore, covariance of x and y is 0, which implies that x and y are uncorrelated. However, y is a function of x which is mod of x, and it can be immediately checked that x and y are not independent. So, this is a very straightforward verification. Please convince yourself that in this example x and y are not independent. Okay. So, let us move on and consider another exercise. So, we go look at exercise 4. So, here we have the structure of independent random variables, and earlier we have seen that if we are dealing with random variables which are in L2, then their product x times y will also have finite expectation. So, this was following from Holder's inequality. Now, we are going to extend that observation when x and y are independent and are in L1. So, and this will require some application of Fubini's theorem, which we discussed earlier in week 2. So, let us see. So, we are taking two random variables x y in L1, meaning we are assuming expected value of mod of x is finite, expected value of mod of y is also finite, and we assume that these random variables are independent. Here what we can do? We can look at the joint distribution of x comma y. Here, as long as these are independent, the joint law can be expressed in terms of the marginal laws as in terms of product of the individual one dimensional laws, right. So, this we have discussed earlier in week 2. Now, we note that expected value of mod of x, which we assume to be finite now because x belongs to L1, that can be expressed in terms of an integral over the law, alright. So, here it is an integration over the real line for the function mod of x, and that quantity we are assuming to be finite. A similar statement is true for the first absolute moment of y, which is now finite, and that can be expressed in terms of this integration over the law of y. Now, both these quantities are finite, and here what we can do? We can appeal to Fubini's theorem, which we discussed earlier in week 2, and observe this set of calculations, that expected value of mod of x y, first of all it is this integration of the random variable mod of x times mod of y with respect to the corresponding probability measure. Now, let us simplify this by changing variables, and here we will go to R2 and we will end up with the joint law of x y, and we are now integrating the function mod of x y over R2 with respect to the joint law. But if x and y are independent, then the joint law factors out. But note here that the integrand that we are looking at, that is a non-negative function, and the integrand is separated into variables. So, therefore, using Fubini's theorem we can separate them out, but each integral separately are finite. So, therefore, the whole quantity is finite. But we have started by looking at expected value of mod of x y, which we have shown now to be finite, and therefore, x times y has to be in L1. So, here we have explicitly used the fact that my integrand is non-negative, and we are appealing to the Fubini's theorem in order to simplify this double integral into the product of one dimensional integrals. Now, we are going to appeal to Fubini's theorem again and look at expected value of x times y now. So, we have already shown the existence of expected value of mod of x y, which is finite now. So, therefore, expected value of x y will turn out to be a real number in this setting. Now, as per definition, this is the integration of x times y with respect to the probability measure p. So, if you again change variables, we will go to the joint law of x y, and the integration will be on R2 function x times y. Now, again the integrands are separated out, and therefore, by appealing to Fubini's theorem, since our functions are jointly integrable with respect to this joint law that we have already established when we showed that expected value of mod of x y is finite, we can appeal to Fubini's theorem and split the double integral into two one dimensional integrations like this, but both the quantities are actually going back to the expected value of x and expected value of y respectively, and both of these are real numbers, and we have ensured the equality that expected value of x y is the product of the expectations. So, here what we have used is the Fubini's theorem together with the independence of the random variables, and we have justified that the product of the expectations will give you expectation of the product of the random variables, and this can be extended to functions of x y also. So, as long as expected value of f of x, that is a real number provided that f of x is in L 1. Again, if g of y is also in L 1, the expected value of g of y will be finite, and in this setting you can look at expected value of f x times g y for functions f and g defined on the real line, and therefore, we can write it as a product. All right. So, these kind of product relations extends as long as you have independent random variables with the appropriate integrability. Note again, the Holder's inequality allows us to do this kind of calculations when we are working with L 2 random variables. Using the Fubini's theorem, we have just extended that, and we have relaxed the assumption from L 2 now to L 1. All right. So, let us continue. So, we further discuss some interesting observation in relation to finite sums of random variables. So, here we first start with a sequence of random variables converging to 0 in the LP setting. Now, here we choose our p between 1 and infinity, both 1 and infinity are included. Now, if x n's go to 0, then the corresponding norms must go to 0 as n goes to infinity. Now, here let us look at the corresponding sample means. So, again recall S n denotes the sum of first n many random variables. So, S n over n is the sample mean. Now, let us try to estimate the p norm of S n by n. Let us write down the expressions. So, since we can bring out this non-negative scalar, we will just end up with this sum of the random variables, and using the triangle inequality we end up with this estimate for the p norm of S n by n. Now, here note, since the p norm of x n's go to 0, by our earlier lemma that we established for real valued sequences, we will conclude that the corresponding norms S n by n must go to 0 in LP. So, here we are using the fact that if we have a sequence of real numbers converging to 0, then their sample averages that we consider must also go to 0. So, and we are applying it to the norm sequence. The norm sequence is a real valued sequence which by our assumption here converges to 0. Therefore, the corresponding averages of the norms also go to 0 as n goes to infinity, and consequently S n over n, which is now the sample mean of this sequence of random variables, that goes to 0 in LP as n goes to infinity. So, let us look at further properties of such sample means. Suppose I have that this sample mean goes to 0 in the convergence in probability setting. Now, we can look at the nth random variable divided by n, and we can manipulate in terms of the corresponding partial sums. So, S n here is the sum of x 1 x 2 up to x n, and S n minus 1 we are going to look at the sum up to x n minus 1. So, that is what we write down. The relation is now giving us the difference in terms of the S n and S n minus 1. Now, here we do further manipulation and write this term here division by n minus 1. So, we have to multiply by n minus 1 here again. Now, treat n minus 1 over n as a degenerate random variable and observe that these degenerate random variables converge in probability to 1. In fact, this convergence holds almost surely. Now, we appeal to algebraic properties of convergence in probability and observe that S n by n by our assumption goes to 0 in probability, S n minus 1 over n minus 1 that also goes to 0 in probability, and if you multiply by this sequence n minus 1 over n that converges to 1. So, therefore, we have 0 minus 1 times 0 in the limit, as convergence in probability has this nice algebraic properties. So, therefore, the actual limit turns out to be 0 and we conclude that if S n over n, which is the sample mean, if that converges to 0, then x n over n must also converge to 0 in convergence in probability setting. Here we now look at some further properties involving such sample means, but from the perspective of almost sure convergence. Here we have seen earlier that if x n converges to 0 almost surely, then the sample means must also converge almost surely to 0. We are going to show by an example that a similar statement is not true for convergence in probability. So, here to do this, what we consider is a sequence of independent random variables now with certain specified distributions. What we do is that we look at for n any positive integer, the value 2 power n with probability 1 by n and value 0 with probability 1 minus 1 over n. So, that is how we get the description of the law of the random variable x n. Now, in this setting observe that if we look at x n minimum 1, then it will be taking the value 1 with probability 1 by n and 0 with probability 1 minus 1 by n. So, this is true because 2 power n will be bigger than 1 for all n. So, therefore, this quantity is 1 with probability 1 by n and takes the value 0 with probability 1 minus 1 by n. So, in particular if we look at the expected value of this bounded random variable, that is 1 by n and goes to 0 as n goes to infinity. So, since this is an equivalent condition for convergence in probability, we will conclude that the sequence of random variables that we are considering here must converge to 0 in the sense of convergence in probability. Now, it can be checked that S n over n in this setting, the sample means do not converge in probability to 0. Alright. So, please check this. So, this will show that even though the sequence of random variables converge to 0 in probability, the corresponding sample means does not converge. Alright. So, therefore, in this week we have looked at further properties of the 3 modes of convergences of random variables. In particular, we have focused on uniqueness of limit, metrizability, algebraic properties and the continuous mapping theorems. We have also looked at finite sum of random variables, and from that we have also tried to look at series of independent random variables. In this lecture, we have covered some explicit examples and exercises illustrating the results of this week. We are going to stop here. We are going to continue the discussion next week. Thank you.